Okay, I think we are good to come, and maybe participants will join during the session. But I would also already like to warmly welcome everybody for today's webinar presented by the GRAPHERGIA project, that is an EU-funded project running in the framework of Graphene Flagship. And in today's webinar, we would like to present to you some research activities coming from GRAPHERGIA, but also beyond, dedicated to laser-based methods for graphene and nanomaterials integration on flexible substrates and electronic devices. This is our 5th session that we organized in our project, and we will have around 1 hour of time to firstly present you some work and then discuss with each other. So during this 1 hour, I'm happy to present you this session. I'm Mona Maril from Australo Marketing Lab. I'm leading the communication and dissemination activities in the GRAPHERGIA project. And today I'm happy to give the floor to 2 professors. First, Professor Spiros Yiannopoulos, who is the coordinator of GRAPHERGIA project, who will present you the project's progress on laser roll-to-roll assisted methodologies to apply graphene on textiles and flexible substrates. He is from Foundation for Research and Technology Helsinki. And then I'm happy to also give the floor to our second speaker, who is an associated professor, Seoung-Ki Lee from Pusan National University in South Korea. And he will give a presentation entitled Laser-Induced Photothermal Synthesis, an Application of Functional Nanomaterials. And at the end, we have some time for open discussion. And firstly, I would warmly like to welcome all our attendees to this session. It's great to see that this topic raises interest for participants for Europe, as GRAPHERGIA is an EU-funded project, but also beyond. We have participants from India, of course, from South Korea, from Egypt and Pakistan, and the EU countries. And as this is a scientific session, naturally the major participation comes from scientific community and research projects, but we have also some representatives from industrial sector. And we have also people from our sister projects, and I would like to warmly once again welcome you all to join the discussion today. Before we kick off the presentation, just some housekeeping issues. We will record the session and share it on GRAPHERGIA's communication channel, so you can have access to it after the session. During the webinar, you can use the question and answer box to share your questions in real time, and we will have time to take them one by one towards the end of the session. And finally, we present this webinar in the framework of our GRAPHERGIA Hub. That is a network of researchers and innovators dealing with graphene and nanomaterials enabled topics related to energy harvesting storage applications. So thank you all for joining us. And before we start, let me just remind you what our GRAPHERGIA project is about. So we are research and innovation action running for 3.5 years. We are now entering our final year of the project. We gather 11 partners from 6 EU countries with the aim to develop innovative pilot lines for sustainable graphene-based flexible and structural energy harvesting and storage devices. We have a budget of 4.5 million euros, and these applications will be piloted on e-textiles, smart sensors, and next-gen lithium-ion battery electrodes. So just to keep it short, this is what the session is about. And now with this, I'm happy to pass the floor to you, Professor Yiannopoulos. Thank you.
Thank you very much, Mona, and also Laura for organizing this webinar. So we are honored today to have Professor Seoung-Ki Lee for the seminar. So before, let me share a brief presentation. before the presentation of Professor Lee, I would like to introduce, I hope you can see my presentation in full screen mode.
Yes, thank you, Professor.
Okay, thank you very much. So, good morning also, or good afternoon, depending on where you are located, to everyone who is attending this webinar. So as I mentioned before, we move to the invited lecture. I would like to briefly introduce the project in whose framework this webinar is organized. So as already Mona mentioned, this is a European project with 11 partners, 42 months duration. The project started in October 2023. So in this slide, I summarized the core objectives of GRAPHERGIA. As you can see, the project is built around two major technological directions. The first one is the smart electronic textiles, where the aim is to move toward batteryless or self-powered wearable systems that can also provide a user-centric interface to the Internet of Things using wireless sensor signaling. The second direction is about lithium-ion batteries, where the project develops laser-based dry electrode fabrication approaches, especially for graphene silicon-based anode materials for lithium-ion batteries. Here you can see the project structure in a more operational way. Both directions I mentioned before start from a common basis. This is the laser-based technology for graphene electrodes. So from this common platform, one branch, the upper one, as you see in the slide, develops process optimization for flexible substrates, then energy harvesting layers, advanced power management integration, and finally, signal processing and IoT prototyping for smart textile systems. The second branch at the bottom focuses on the optimization of lithium-ion batteries, especially anodes, followed by cell design and assembly. And then also an important part of the work is to study the aging mechanism and benchmarking of the battery cells. So around all these technical directions, there are also other activities. As you see here, the project integrates very strong dissemination and communication activities conducted by Australo, also IPR management by Glotia IP, and also life cycle assessment by Next Technology. So as you can see, this gives to GRAPHERGIA a full chain from material synthesis to device and system validation. Actually, one of the most important practical dimensions of our project is digital manufacturing. So this slide shows a picture from a roll-to-roll pilot line we're developing in collaboration with Adamant Composites and SME, located very, very close to Fourth Institute, where you can see here that this line combines precursor deposition, dry processing, graphene growth by laser patterning, the precursor. And this is a very, very important step because it brings graphene-enabled devices very close to scalable industrial implementation. So the approach, we consider that this approach is attractive not only for performance reasons, but also because it supports reduced use of critical raw materials and also minimizes any toxic or pollutant intensive processes because this is a laser-based technology. So in order to better appreciate the scientific relevance of the invited lecture that we have today by Professor Lee, I will very briefly step back, let's say, in history and place GRAPHERGIA within the wider evolution of laser-assisted graphene synthesis. So maybe this is not very well known to everyone, but preparing, let's say, graphene using laser beams is not so new. This slide reminds us that the scientific roots of the field are much older, let's say, than 15 years ago, where the first term LIG appeared in the literature. So already in 80s and the early 90s, we have some fundamental studies of UV laser ablation or excimer laser radiation of polymer materials and especially Kapton polyimide. The main idea at that time was to prepare conductive tracks on polymeric films. The researchers at that time were able to produce porous, electrically conductive, and patternable carbon layers on the surface of these polymers. So actually, these earlier studies established the groundwork for the laser based transformation of polymers into conductive graphite carbon structures. So you can understand that long ago, before the popularity of the LIG, the laser-induced graphene term was coined, the main physical and chemical principles were already emerging from such studies. In this slide, I try to summarize a few major milestones in the, let's say, most modern development of laser-induced graphene era. So in 2012, in our group, we used CO2 laser and managed, let's say, to prepare epitaxial graphene on silicon carbide wafers by a simple method which is shown in the schematic here. The method took place at ambient conditions. And the method was based on the rapid photothermal graphitization of silicon carbide. The composition of silicon carbide, let's say, removes silicon and the remaining carbon reconstructs to epitaxial graphene. And then later in our group, we extended this the composition of silicon carbide to particles. And this opened actually the way toward the graphene-based battery anode concepts that we are using now in GRAPHERGIA. In the same year, in UCLA, the group of Kanner demonstrated for the first time laser-scribed flexible graphene-based electrochemical capacitors based on reduction of graphene oxide. And in 2014, the RISE team of Professor Tour also used the CO2 laser for processing Kapton foils, an idea that, as I mentioned before, was mostly known, let's say, from the past, although that time the term graphene was not popular at all. As you can understand, since let's say 2014, when the LIG was popularized, the field has been expanded enormously in terms of, let's say, different wavelengths of lasers, different atmospheres of the process, substrates, dopants, and applications, of course. This slide is just to provide you a visual reminder of the early works of this field. So you can see here that already in 1994, 20 years before the term LIG was coined, researchers were able to use UV lasers to irradiate Kapton and provide what we know today as three-dimensional porous graphene-like structures. So this is important because it shows that laser-driven conversion into conductive carbon networks has some, let's say, deep roots. So it did not suddenly appear as a completely new concept in the recent years. In our lab, we have developed, let's say, and protected by international patent, a new method how to prepare graphene, which is, let's say, not adhered on the Kapton substrate, but graphene which is at the same time produced and transferred on an acceptor substrate. So this last method, laser-assisted explosive synthesis and transfer, is a very versatile method because in this case we avoid the manual transfer of graphene, which is grown, for example, on Kapton for using, let's say, on another substrate, and we can directly deposit high quality graphene on the substrate of interest. So this method can be used, as you can see here through these images, to prepare 3D porous graphene-like structures, or if you, let's say, select multiple precursors. So in the same, within just one lasing event, you can produce hybrids of nanoparticles covered by graphene-like materials. This is my last slide for this short introduction, which shows how broad is now the field. As you can see here, laser-assisted graphene synthesis and processing today, let's say, span many laser sources, wavelengths, pulse durations, technological approaches, and the processes also include direct laser writing, scribing, irradiation, and other processing modes. So this broader context is exactly why the seminar we have today, the invited lecture, is so relevant also to GRAPHERGIA. So now it's my great pleasure to introduce Professor Seoung-Ki Lee from Pusan National University. As you will see in his presentation, part of his work is highly relevant to the core concepts of GRAPHERGIA, particularly in relation to the laser-scribed selective synthesis, nanomaterial integration, and next-generation device fabrication. So, Professor Lee, dear Seoung-Ki, thank you very much for being with us today, and the floor is yours.
Okay, thank you for kind introduction. Okay, I will share my slide from now. Okay, can you see my slide?
Yes, perfect.
Yes, we can do.
Okay, okay, let me start. Thank you for the kind introduction. My name is Seoung-Ki Lee from Pusan National University. It's a pleasure to meet you all, and I would like to thank you for giving me this opportunity to share my research at this meaningful webinar. Today, I will talk about the laser-induced photothermal synthesis and application of functional materials, specifically focused on 2D-based nanomaterials. This is the outline of today's talk. First, I will discuss the selective synthesis of sheet-structured 2D material, and then introduce 3D structured graphene. Okay, let's start with the sheet-structured 2D material. When I was young, I had to use a bulky computer with a large CRT monitor. There was hardly any space left on the desk, and it was very difficult to move. At that time, when I need a new computer, I only consider its performance, such as speed and storage capacity. However, things have changed significantly. Computers have become smaller and lighter, allowing us to carry them anywhere. For this reason, when we buy a new device today, we consider not only the performance, but also convenience and portability. So, what do we expect from future electronics? Maybe that is creativity, right? Unlike current device, when we input some information to the computer, we expect them to generate the insight or even opinion through the artificial intelligence, as like GPT. So to satisfy the consumer's requirements, many researchers are working intensively at both the transistor and the system level. At the transistor level, as scaling in planar structure has approached its limits in maintaining the Moore's law, 3D device architectures have been introduced and have continuously improved the performance. Although this approach involves extremely complex and fine process, but it is the best option until now. At the system level, advanced packaging technologies have also been developed to go beyond the Moore's law. This includes the integration of heterogeneous devices to achieve performance that exceed the limit predicted by Moore's law. When you check the roadmap of the leading global semiconductor companies, we can gain more detailed insight. Based on the TSMC's roadmap, they are considering new channel materials following the development of 3D device architecture. Similarly, Intel and IMEC are also considering similar development strategies. The key point is that although these companies have different technologies, they are all considered the 2D materials as candidates for post-silicon electronics. So when you check when you scan the development history of 2D materials, we see that since 2004, when graphene was first exfoliated from the graphite, the production scale of 2D materials has increased dramatically. In addition, as it has been revealed that the physical property of these materials are close to their ideal limits, a new device concept has continuously been developed. More specifically, as shown here, two-dimensional materials are being applied not only in a logic device, but also in cutting-edge electronics applications. In case of logic device, with the help of wafer scale synthesis and transfer technology, new type of device have been reported. Recently, MOS2-based 3D architectured transistor was also reported by TSMC. Furthermore, advancements in flexible driving circuit and sensor that can be attached to human skin are good examples of flexible electronic applications. These developments also suggest a strong potential for synergistic integration with the conventional semiconductor technology of 2D material. Overall, although the demonstrated technology and the application appears highly advanced, one important point to notice is that all these achievements are based on the single type of two-dimensional material. However, when we integrate the 2D material to form heterostructure, we can enable more diverse and creative research opportunities. 2D-based heterojunction devices are opening the new field from the optoelectronic to the biology beyond the capability of the conventional materials. However, there is a key challenge in there. Although many devices show some promising performance, most results are limited to single device as shown in this slide. This is because it is extremely difficult to fabricate a uniform 2D heterojunction device array. This limitation is a major barrier to practical applications. From an industrial perspective, uniformity is more important than the peak performance. Device fabricated at different time must exhibit the consistent characteristic. Although this may seem simple, but it remains a challenge. In this work, I focus on identifying the root cause of this issue from the perspective of material synthesis. So here I summarize the 5 general preparation methods for transition metal dichalcogenized. Among these 3 methods are most widely used method: chemical exfoliation method, thermolysis method, and chemical vapor deposition. The researchers are studying the electrochemical property of TMDS typically use chemical exfoliation or thermolysis method. In contrast, those working the electronic device applications usually synthesis TMDS using CVD, this method. As I'm also a researcher using TMDS as an active channel material in electrical device, my work also is based on this CVD process. The development of CVD technology has been rapid and remarkable. Before the 2000s, researchers focused on large area synthesis of high-quality 2D materials on mother wafer. However, due to the need for the transfer process, attention has shifted toward the direct synthesis on the target substrate. In particular, low temperature and the clean process are gaining increased interest. Recent studies have demonstrated the synthesis below this 2D material below 400 Celsius, enabling integration with the CMOS device and flexible substrate. Despite this advance, one limitation remains, that is the narrow synthesis window of this approach. In this region, reliability achieving high quality material is still challenging for many researchers. Even now, most researchers rely on the wet or dry transfer process to fabricate the 2D electronic device. The challenge begins at the very first step of device fabrication. To build even a basic device such as this image, the 2D material should be separated from the mother wafer and then transferred onto the target substrate using a supporting layer. During this process, defects such as wrinkles and bubbles are formed at the interface. After transfer, patterning and etching are required to define the device structure. But these steps can leave the unintended residue on the surface. These residues lead to the unstable contact with the subsequent layer. To mitigate this, additional thermal treatment cleaning processes are often applied. However, such treatments can damage to other components on the device. So device frequently exhibit the non-uniform performance due to residue contamination and unintended doping effect. These issues become even more critical in the heterojunction structure, where the multiple layers should be integrated on edge like this kind of images. So these issues are not limited to a few research groups. Even in the well-equipped companies and research institute, device uniformity remains a challenge also. When you check the reported result, each device often shows the variation in each cross-sectional structure. As shown in here, when comparing the device within an array, unintended variation degrade the uniformity of their electrical property. Therefore, to bring 2D materials into real-world application, three key challenges must be addressed. First, device uniformity must be improved. Second, the thermal budget must be minimized. And if the solution is a simple and cost-effective method, it would be better. Interestingly, we already have the direction of solving these challenges. To improve the uniformity, we need the residue-free process, meaning the direct synthesis of nanomaterials on the target substrate. And to minimize the thermal budget, heat energy should be applied in some confined area. Maybe it is not perfect, but we propose a solution based on laser-driven thermal treatment. We believe that many of these issues originate from the global heating system of the CVD process. Therefore, we replace the thermal furnace with a laser as the heat source to enable localized heating. Because lasers have monochromic wavelengths and high temporal and spatial coherence, we can selectively hit the specific region of the target substrate. For example, even in the stacked three-layer structure, it is possible to selectively hit the mid-layer if it has a higher absorption at the laser wavelengths. In addition, due to the directional nature of the laser beam, we can directly pattern the target material by scanning or drawing the laser beam. So I bring a short video that explained our research concept. Unfortunately, 2 years ago, graffiti was written on the wall of old palace in Korea. To remove it, a laser-based selective etching technique was used. Because the laser wavelength is strongly absorbed by the paint, only the paint can be thermally removed with the minimum damage to the underlying stone wall. Okay. Similar to this mechanism with the previous video, we propose a low temperature photothermal treatment method using laser system. The basic synthesis mechanism is similar to the conventional thermolysis method, as like this below the image, but there are two key differences. First, we selectively anneal only the desired region using the laser instead of hitting the entire substrate with the thermal furnace. Second, we use the fiber laser with the wavelengths of 1.06 micrometer. With this condition, we can directly pattern the 2D materials such as MOS2 and WS2 without the residue in simple and fast process. The procedure involved just 3 steps. First one is spin coat the precursor, and then laser scribing, and then solvent washing to remove the unexposed region. By repeating this step, we can fabricate the additional 2D material and build a more complex structure. This approach for synthesizing MOS2 is quite similar to the LTPS and LTPO process, so we denote this method as LTPT. Here, the T represents the transition metal dichalcogenide. The process is simple, but the key factor is the selection of the laser. When we use the fiber laser in this system, we can avoid the damage MOS2 due to the significant difference in absorption between the precursor and MOS2. As shown in here, the absorption differ by about 3 orders of magnitude. Therefore, the fiber laser efficiently hit the precursor layer. However, once the precursor is thermally converted into the MOS2, the further heating is suppressed because the laser light passes through the MOS material due to its low absorption. When we evaluate the quality of this MOS2 and WS2 using Raman spectroscopy, we observe the sharp peak compared to those of material synthesized by conventional CVD method. To support our synthesis mechanism, we simulate the heat distribution across each layer under the laser irradiation. The results showed a cross-sectional view of our sample structure. A 300 nanometer silicon oxide layer is formed on the silicon wafer, and then the 20 nanometer precursor layer is coated on top. Under this structure, when a laser pulse is applied to the sample, the temperature of the precursor rapidly rise to over the 700 Celsius due to its high absorption at the laser wavelengths. In contrast, the underlying silicon oxide and the silicon layer remain at the relatively low temperature. Although some heat is generated in the silicon layer, it is effectively blocked by the silicon oxide due to its low thermal conductivity. These results indicate that the fiber laser can selectively hit only our target precursor layer. With this material selective and directly patternable heat treatment method, we can realize several advanced applications. The first is ultra-fast and cost-effective device fabrication. In conventional process, semiconductor material are typically deposited over the entire wafer. However, in our approach, we selectively synthesize the micro-scale MOS channel pattern using the laser irradiation. As a result, it takes only 5 minutes to fabricate 1,600 active layers. In contrast, producing the same array using the conventional CVD method would take several hours and may introduce the wrinkle and residue on MOS2, as I mentioned the introduction part. And our method are not only reduce the processing time, but also eliminate such issues. So the advantage is clearly reflected in the device performance, as shown in transfer characteristic. Using an ion gel gate dielectric, the device exhibits the highly uniform behavior without the additional cleaning process. The exacted mobility and the on-off ratio is approximately 6 and 10:3, respectively. The second advantage is that the demonstration of 2D-based heterostructure. As mentioned earlier, our method enabled the selective thermal annealing of the precursor layer while minimizing the damage to the surrounding materials. Using this approach, we can easily stack the WS2 layer on the top of MOS2 layer. The process is simple. First, MOS2 is synthesized on the silicon oxide wafer, and then WS2 precursor is coated on the top of MOS2. When the fiber laser is irradiated, the precursor of WS2 is pyrolyzed and they convert into the WS2. Due to the low absorption of both MOS2 and WS2 at the laser wavelengths, the underlying layer remained unaffected. Therefore, a P-type WS2 and N-type MOS2 heterostructure can be successfully formed. Raman mapping confirmed that the high quality of both layer and the formation of the well-defined PN junction at the overlapped region. Electrical measurements reveal clearly reflecting the behavior of this forward and reverse current ratio, rectifying behavior with the forward and the reverse current ratio is almost 10:3. Using the same approach, we can also demonstrate this kind of MOS2 graphene Schottky junction. So in this process, we firstly form the graphene layer, and then using this laser ablation method, we stack the MOS2 layer directly on the graphene. I would like to introduce another advantage of our method in the field of flexible electronics. As mentioned earlier, atomically thin two-dimensional material have a strong potential for flexible device. However, conventional approaches typically require the synthesis on the rigid wafer, followed by the transfer to a flexible rubber substrate. In our work, we overcome this kind of process limitation. Two-dimensional material can be directly synthesized on the rubber substrate. As shown in here, we first coat a PSAF rubber substrate on the precursor, and then apply the same laser annealing process as shown in here. The fiber laser penetrates the rubber without causing the damage and selectively heat up the middle layer of MOS2 precursor and converting it into the MOS2. After etch out the underlying silicon oxide layer, we can directly obtain the MOS2 device on the rubber substrate, as shown in this photo. This slide shows the result of the flexible motion sensor based on MOS2 film synthesized by laser annealing method. To detect both the magnitude and the direction of the strain on the wrist, we designed this rosette gauge structure consisting of the 3 strain gauge arranged at 120 degrees. Because our process does not involve the transfer or complex fabrication step, we were able to place the device precisely at the desired location. Compared with the conventional transfer method, sometimes it caused this kind of misalignment during the transfer process. But in our case, we can put the device on the exact position. So each sensor can exhibit the nearly ideal performance. And then thanks to this high level of uniformity, the flexible sensor can accurately detect the direction and the magnitude of strain of our wrist. Okay, let me briefly summarize my talk. To realize a practical device based on two-dimensional semiconductor materials, there are 3 key challenges to address these issues. Our group has developed a laser-based selective thermal treatment method that enables localized heating of only the target layer. Using these approaches, we have achieved results that are difficult to obtain with the conventional CVD synthesis technique. Okay, from now on, I will introduce another method for synthesizing 3D structured carbon materials using laser as part 2 of this talk. Okay, Professor Spiros already mentioned about this material. This material is called laser-induced graphene, LIG. It is typically synthesized by laser-induced heat treatment of polymer substrates such as polyimide. Because the thermal decomposition reaction is rapidly, and then gases generated during the carbonization of polyimide from porous carbon structure as shown here. In our work to control the structure of LIG, we tune the power density delivery to the polyimide by adjusting the focal length of the laser. In other words, under direct focus, high energy is concentrated within the small area. In contrast, under the defocus condition, the laser energy density per unit area decreases, and at the same time, the laser spot overlaps, enable the control of heat accumulation using this method. As a result, both the carbonization rate of polyimide and the degassing rate change, allowing us to tailor the LIG structure from porous to fibrous form. As shown in here, we can, using this kind of defocusing method, we can control the structure of LIG from these porous structures to the fibrous structure. As shown in this cross-sectional image, the fiber-shaped LIG exhibit the length exceed the 300 nanometers, and this can be controlled by the simple parameter, means that the focal length of the laser. In this case, not only the structure, but also the crystallinity and the composition of LIG are also changed. Here, we refer to the conventional LIG as a porous LIG, and the LIG with the long fiber structure as a LFLIG. As shown in this Raman analysis, the fibrous LIG exhibit increased the defect density, and the crystallity size gradually decrease as the structure becomes more fibrous. This slide shows the result of XPS analysis. As the structure changed, the internal composition of LIG is also modified, which in turn affect its work function. As shown in this UPS result on our result on the right image, the work function gradually decrease as the LIG become more fibrous. Based on this characteristic, means the increase the surface area and reduce the work function. We implemented a nanogenerator using this fibrous LIG electrode. By comparing the triboelectric series with the work function of LFLIG, we identified PMMA as the most suitable counter electrode. Accordingly, we fabricate the nanogenerator device using these material combinations. This slide shows the performance of the nanogenerator based on the fibrous structures LIG and PMMA as the counter electrode. As shown in this figure, LFLIG exhibit approximately 130 times higher output performance compared to the porous LIG. This improvement can be attributed to the increased surface area and the change in the work function arising from the fibrous structure, as mentioned earlier. And also, our group further utilized these characteristics to implement an array type of device. So this slide shows the demonstration of a 4x4 LIG TENG array capable of positioning tracking. Due to time limit, I will briefly go over this part. Next, I will introduce another research topic from our group, which involved the direct synthesis of porous carbon supports on the silicon semiconductor wafer. As shown in this figure, instead of using the conventional PI film, we use the photo-patternable polyimide material. So through the photolithography process, we define the area of this polyimide film on the silicon wafer. And then when a CO2 laser is irradiated on here, only the polyimide layer is selectively converted into the graphene, porous graphene. So here also the key point is using the different absorption property between the polyimide and then bottom substrate. Means the polyimide has high absorption of this CO2 laser, but silicon oxide and silicon can be penetrated that laser beam. So as I mentioned, the key point of this process is using the CO2 laser in this system. And also, we checked some cross-sectional image of 3D porous graphene as shown in here using SEM. This 3D porous graphene is tightly attached, means bond with the silicon without the gap between there. And also, it also shows the porous structure as like a conventional LIG system, and Raman XPS result also shows the even though we're using the photo pattern of a polyimide film and then form the LIG on the silicon oxide wafer, the overall characteristic is similar with the conventional LIG material. The fabricate the three-dimensional porous graphene and silicon make Schottky barrier junction. So we can use this kind of Schottky barrier junction device as a photo detector. As you may expect, porous graphene exhibit very high light absorption with minimal reflection, leading effective photo conversion effect. So briefly, we compared some reflectance of porous graphene as shown in here. Conventional film type of graphene has a high reflectance in this system. But when we form the porous carbon material on the silicon, the overall surface reflectance is decreased under 10%. It means that this device can effectively absorb the outer optical energy. In addition, due to the multiple scattering within the porous structure, incident light from the various angles can be effectively absorbed in this Schottky junction device. As a result, the device shows a high detection efficiency over the wide range of incident angles. In this approach, we have recently advanced the technique one step further. Specifically, we introduced the laser ablation in solution to selectively functionalize porous graphene. As shown in this figure on the left, by locally positioning the dopant solution and inducing the laser and then induce some reaction, we can achieve the selective chemical doping of porous graphene in this system. Based on composition analysis and transistor measurement, this method enables tuning of the graphene from N-type to P-type material. It means we can chemically dope the LIG using this system. In addition, by incorporating the metal precursor into the dopant system solution, we can also synthesize porous graphene decorated with the metal nanoparticle as shown in here. So one of the advantages of this confined liquid ablation method is when we expose the laser, the liquid phase of dopant is continuously fed at the reaction site. So we can get the uniformly dope the LIG system in the depth direction. By employing this solution-based laser ablation technique, we can realize active matrix device that were previously difficult to achieve with the conventional LIG system. Until now, there have been several key limitations to realize the active matrix device based on the LIG. First one has the challenge to the precisely patterned porous carbon structure, and second is there has been no reliable method for selectively doping. Finally, forming a stable electrical contact with the three-dimensional carbon structure has also been difficult. By overcoming these challenges, our group has demonstrated two representative applications. On the left side, we present the integrated sensor platform consists of an array of functional gas sensors on the single substrate. This is the first demonstrated of integrated LIG-based devices with the diverse functionality on a single substrate, enable the selective detection of the various gas systems. On the right side, we show the first implementation of LIG-based CMOS system by integrate the N-type LIG transistor and P-type LIG transistor. Since this work is not yet published, I will briefly explain about this part, and then if I have another chance, I will explain more details. So due to time limitation, I apologize for not being able to explain everything in detail. And thank you very much for your attention. And I would like to thank you, Professor Spiros, for the invitation and my students for their contributions. With that, I will conclude my presentation. Thank you.
Excellent. Thank you, Professor Lee, and to your group for sharing these great insights from your work. Now it's time for open discussion. So if any participants would like to have any open questions, you can tap your question in that question box. For the moment, there isn't any, or you can just basically raise your hand and I can enable you to present your question by speaking. So if there is any questions now, it's time to raise your hand. Or Spirit, if in meanwhile, Professor Yiannopoulos, if you would like to comment on the presentation we just saw, of course, that's okay.
Yes, first of all, Seoung-Ki, thank you very much for this very, very important and insightful talk, which covered a very broad range of important topics. It was really very stimulating and very, very interesting, I think, for all the people. So I can start with a brief question until other people, let's say, make up their minds. The the idea of transforming ammonium threomolybdate to MOS2 with a laser is very important. In this case, are there other precursors, or you are very limited, let's say, to this single precursor to prepare the MOS2? In graphene, we know we can have many different precursors from biomass, polymers, etc. In your case, typically the choice is very limited. Is this a problem, let's say, in developing the field, or you think it works very well?
Okay, so I will share. So you mentioned about this part about the precursor of this system, right?
Yes.
Yeah, as you mentioned, it is not easy to find the suitable precursor to apply this system. So currently, I found some precursor for MOS2 and WS2, and Sigma Aldrich. We can both some the other type of telenum-based precursor, and also I also some the researcher who can synthesize the precursor who is expert at chemistry. I asked to them to synthesize a new type of precursor to apply this kind of laser ablation system.
Okay, thank you. And are there any? I mean, MOS2 is known to readily oxidize, so compared to graphene, which is very stable. And then the attachment to the human skin also raises concerns on toxicity. So what are your thoughts about it? I mean, it can be very sensitive as a sensor, but it has also these disadvantages. How do you cope with these points?
Yeah, that is a really important question. So frankly, when we synthesize MOS2 using this method, we can simply synthesize MOS, but the weak point is the grain size really, really small. So as you mentioned, it is weak at the oxidation process. So to maintain the electrical property, we should make some protection passivation layer on the MOS2 layer. In that case, we can avoid some toxic issues when this sensor attached on our skin. Yeah.
Yeah, yeah. Thank you. I don't know if there are questions yet. I can continue, Mona, with a couple of questions to.
We have sorry, if you check the question and answer box, you can see that we have 2 questions there. So the first one, and you can see it written as well in the box. How reliable are the porous graphene, for example, with the scratch test? Is it really useful for long-term applications?
Yeah. That's also important question. And then, yeah, as the Suraj, maybe Suraj can expect the weak point of this kind of LIG system. So this LIG, especially in case of this fibrous structure, it is really weak at some scratch. But relatively, the porous graphene can maintain the its. I'm not sure. Maybe not exactly maintain its structure. You can expect the top layer of LIG is really weak at the mechanical stress. So so in my case, so I tried to demonstrate some nano generator, just the pushing motion. So without some slip or some scratch motion. So in this case, this porous LIG or fibrous LIG can almost maintain its structure. And then.
Perfect. Then I have one person who is raising hand. So Hirali, normally Hirali, you raised your hand and you're able to comment now.
Or thickness of deposition. So what about the surface area of 3D porous coming from?
Okay. So yeah, let's take the second written question. Maybe the microphone is not working. So can you comment about the thickness of deposition? What about the surface area of 3D porous carbon from polyimide using LIG? Which features of the material is responsible for triboelectronic behavior?
I can. So generally, it depends on what kind of polyimide used in this system. So generally, when we using the okay, sorry. Okay, I'll check that. Generally, when we synthesize LIG on this kind of polyimide system, in porous LIG system, the surface area is around 400 or 500. I'm not sure, but Professor Spiros, do you know that exact surface area of LIG?
Yeah, I think in the literature depends between 150 and 500 depending on the way you produce it. Yes, but it's a few hundreds square meter per gram typically.
Yeah. It depends on some structure of the LIG. Yeah. So it has some broad range of surface area, and then which feature of the material, which of the material responsible for the. So the answer about which feature of the material responsible for triboelectronic behavior. So, could you ask more detail about this question, Joseph? So you remain which feature of the material responsible for tribal? Okay, I will explain you in this. So when we get the high performance of triboelectric material, we have to use the most two material that has a positive side material and negative side material. So when you choose the PMMA and the PTFE, we can get the high performance TENG. But in our case, the work function of our LIG is positioned between the acrylic and polyimide this position. So when we consider some difference potential between the positive material and negative material, so we choose the PMMA as a counter electrode in our system. So when you design the TNG, you need to check this kind of triboelectric series on the website. Okay.
Perfect, thank you. And I think we have one more question in the question box. Thank you people for being reactive. This is what the session is all about. So this comes from Faizan Ahmad. Can you comment on this that you are able to use sapphire substrate for heterostructure because SI is amorphous in nature?
Yeah, that's also really good question. So frankly, there are two parts in my presentation. So when I synthesize the MOS2, in this case, the lattice mismatch, when I use the sapphire substrate, the top MOS2 film has more high crystallinity due to the crystallinity of the sapphire substrate. So, but in this system, I just using the silicon oxide wafer to show some universality of this system. And also if I using the some LIG in this system, I think we have to consider some thermal coefficients of the sapphire substrate, because the main mechanism of this process is depend on the heat accumulation. So if the sapphire shows more has more better thermal transport property, that easy to form some LIG on the sapphire substrate.
Okay, great. Thank you for that answer. And finally, I can see that there is one person who would like to speak up. Kapil Porkar, the floor is yours. Normally, Kapil, I enabled you to speak if you want to ask your question.
Hi, can you hear me?
Yes, thank you.
Yeah. Great presentation, Lee. Thanks. So I have two questions, mainly about MOS2 synthesis. First, how do you think how easy is it to control the thickness of your MOS2 or WS2 layers when you are using a laser for fabrication? That's one. And second, as you mentioned, the crystal sizes are very small. So when you make a film of any dimension, that are going to have multiple grain boundaries, which is a very crucial when it comes to the electrical transportation and hence the performance of devices. So what do you see, how do you compare the performances in comparison to the CVD grown single crystal MOS2?
Yeah. Oh, that both question is really harsh to me. Yeah. First question, due to the time limitation, I didn't put some thickness information of the MOS2. So my target is synthesis the monolayer of the MOS2 using this system. But as you can expect, the laser ablation process is really harsh. So I cannot get the mono and bilayer of the MOS2 film. Frankly, partially I can get that kind of thin MOS2, but to get some film type of MOS2, the minimum thickness is 3 layers of MOS2. And also the crystal size. So currently we are conducting the additional modification of our process. So put this system in some vacuum chamber and then finely control the laser parameter. So to increase the grain size of the MOS2 and then to improve the mobility value using this system. But until using this original process, the grain size is almost under the 50 nanometer. But when we precisely control the grain size, we can increase that grain size up to almost 90 nanometer, still smaller than 100 nanometer. And compare with some conventional CVD system, maybe you know well using the CVD system, we can synthesize a large grain size of MOS2. So compared with that system, the mobility is quite low, still now. But the advantage of this method is we can get the high uniform device array using this system. So I try to apply this material using laser synthesis using laser material. I try to apply on the sensor system using transistor electronics.
Thanks. Interesting approach. Thanks a lot.
Thank you.
Brilliant. I can't see any other questions for the moment, so I would like to pass the concluding words to you, Professor Yiannopoulos. Whereas if you have any concluding comments, now it's the time before we close the session for today.
Yeah, but before that, I have a very quick question to Seoung-Ki. Seoung-Ki, the MOS2 produced by laser is a flat crystal or gets somehow 3D-like form like graphene? I mean, how it looks like in SEM?
Oh, sorry.
The MOS2 you prepare by laser, is it really a flat crystal film or it is a 3D-like
Yeah,
such
yeah,
as a graphene? Or how does it
yeah,
look like in microscopy?
yeah. Currently, I also study about the origin of that region. So, firstly, from this SEM image, I can explain about that. When I synthesis MOS using this system, the crystal, uh, uh, it following the surface of the bottom layer. So as you can see here, the crystal is not cross-link. It make this kind of flat crystal structure. So I can say using this method, we can synthesize flat MOS2 film.
Okay, so thank you very much. And as we don't have any more questions, I think this was a very fruitful discussion, very insightful webinar. The topic is very interesting worldwide, and I think the work we presented, Seoung-Ki, is really important. It was very nice. We had, let's say, the participation of the audience with very nice questions. So I think it was a very successful event. So I would like to thank you again, Seoung-Ki, for being here. It's very late in your country, and also you stayed late in your office to present for us. I would also to thank all the audience and also Mona and Laura who organized all the event.